In this video and the next one, we will take a look at networking hardware. So we'll take a look at how switches work, how routers work, and how network interface cards work. Let's start by reviewing what we know about network switches. So switches, we will consider the ones that work at the data link layer or OSI layer 2, and so we'll call them layer 2 switches. Remember that what switches do is they receive frames on one port and they send those frames out the port connected to the destination device, and so they keep track of source and destination MAC addresses, and this is how switches figure out where to send frames. If a switch gets a frame with not just a specific MAC address for the destination, but a broadcast MAC address, which is, as you may remember, all Fs, so that is 6 bytes of FFs, which is 48 bits of all ones, then that means send it out to all systems, all LAN stations on that local area network. And so switches will do that. If you send a frame with the destination MAC address that's all ones, all of the ports get that frame. Okay, switches can operate in either half duplex mode or full duplex. So half duplex means you're only sending or only receiving at any given time. Full duplex means you're sending and receiving at the same time. And that's the advantage, if you remember, that's the advantage of using switches. Unlike hubs can only do half duplex, but switches can send and receive at full speed at the same time. So once again, switches allow connected devices to transmit and receive at the same time, simultaneously, because there is no well, if you just have LAN stations, there is no collision. We'll talk about collisions in a bit. The other thing to note is that if you have a switch, it's usually capable of multiple protocol speeds. So a 100 megabit per second switch can operate in multiple speeds. If you have a LAN station that just so happens, let's say a NIC in a computer is only capable of 1 or 10 megabits per second, then the switch will work at that speed. It cannot, send data to that slower NIC at 10 or 100 if that NIC is only capable of 1 megabit per second. And so a lot of switches would be called like 10-100, that is capable of either 1 or 1-10-100, and so it can operate. If you take, for example, a 10-100 megabit per second switch, it can operate at 10 megabit per second half duplex, that is only sending or only receiving at any given time, or 100 megabit per second at half duplex, or 10 megabit per second full duplex, that is sending and receiving at the same time, or it can do full speed 100 megabit per second full duplex, sending and receiving at this bit rate. Okay. So remember that the nice thing about switches is that when you have a LAN station connected to the switch, then there are no collisions in that scenario. When you have a LAN station connected to a switch, you can have that LAN station send full speed, whatever speed the LAN station is capable of. It has to match, the switch speed has to match the LAN station speed, and it can also receive at that same speed. However, if you have not a simple LAN station but a hub, then you can have collisions, because hubs are just electrical connections. They basically work at layer 1, the physical layer. And so if you have multiple LAN stations connected to a hub and they just so happen to send data at the same time, then those frames will collide. Your frame check sequence won't make any sense, and you will have detected a collision, and then what you should do is just ditch that frame and wait for those two machines to retransmit, hopefully not at the same time. So switches, when they do get, let's say, a signal from, let's say this hub gets two land stations sending at the same time, they will collide. That hub will just send that data, not knowing what to do with it. The hub is a layer 1 device, doesn't look at what's happening with the data. It'll send that to the switch, and then the switch detects that there was a collision, and it won't send that to any of the ports that's connected to it. So once again, switches, if doesn't matter how many machines are connected, you can have a 48 port switch with 48 machines all sending and receiving at the same time. You can have that. However, if you have a hub, then that one connection is going to happen in half duplex, because the hub is half duplex. It can only either send or receive at the same time. It can have collisions, and the nice thing about switches is that that collision does not propagate any further. Okay, so then you may be thinking, well, so how do switches know how to send a frame to a given port? It turns out the key to this is that switches, remember, they're just a computer with many input ports, and so it has programs running on it all the time. And so the main thing switches do is they have a program that keeps track of a switching table, and that is the key to understanding how switches work. So an easy way to think about this is that the switching table has two columns, MAC addresses and the ports that they are connected to. So you could say that a switch table stores pairs of data, and the pairs are MAC addresses and ports. So we can think of this as a table with two columns. That's actually this more complicated, but let's just say for now that it just has a simple table, two columns. We'll talk about some of the other data in a little bit. Okay, so what does this table do for us? Well, it tells the switch where to forward, which port to send a frame out on if it sees a destination MAC address that matches one of the addresses in the table. So let's say this is the switching table. I hope you can read this. Hope the resolution is enough in this video that you can read all these numbers. But if the switch, let's say, gets a frame from this machine over here where the MAC address ends in a 1.5, remember that frame gets sent to the switch. The switch says, let's say you get a frame from this machine and it's being sent to a MAC address that has a destination MAC address that's and ends in a 15. Then the switch comes along, takes a look at the table and says, what is the matching MAC address? And it says, oh, here it is, 005056C02F15. And it says, oh, that's on port 16. All right, and then it'll send that frame that came from this machine to the switch. Says, okay, I know where that MAC address is located. It's on port 16, and it sends that frame to the proper destination. So the table tells the switch where to send a frame, and all it needs is a destination MAC address. It doesn't really care where it came from, but then it actually does keep track of those source MAC addresses, because when you first turn on a switch, let's say it's turned off, powered off, and you plug it in, then the switch does some initialization. Remember, it's just a CPU, and the switching table is initialized to all be empty. There's nothing in the switching table. And then what the switch has to do is slowly learn, and it learns where, which ports are connected to which MAC addresses by observing frames that come in through the various ports. And this is where it looks at the source MAC addresses. So remember that when you send a frame from a land station, it's destination MAC address, source MAC address, and then the data, that's the payload of that frame, and then followed by the frame check sequence, which can be used to detect collisions and all of that. And then so that two pieces of information in the beginning, the frame header, are once again destination MAC address and source MAC address. So if this machine sends a frame, its MAC address 0050056C00001 will be the source MAC address of the frame that it sends out. The destination, if the switch doesn't know about the destination, which let's say is the one ending in 15, then it can do a number of things. It can ignore it, or most usually what happens is that switches will send that frame out on all ports, and so that to ensure that the frame does get to its destination. But most of the time you don't have to do that, because eventually that one destination, which ends in a 15, that LAN station is likely to send a frame out. Eventually, at some point in time, that has to happen, and that's when the switch learns what the MAC address is that's connected to that port number. So it knows the port number. All it needs is one frame to come in on that port, and then it knows that that from the source MAC address what is connected to that port. So that's actually how it learns. It's called learning, but it's really all it's doing is observing frames coming in on each port. It knows what port each frame is coming in on, and it just reads the source MAC address to figure out what should go into the switching table. So once again, as network devices send frames through the switch will read the frame's source MAC address, and then if it's not in the switching table yet, it will add an entry saying, okay, I got a message from 21 on port 3. I'm going to put this in this table. Okay, and if some machine hasn't transmitted a frame for a long time, and that machine is the destination for a frame coming from one of these other LAN stations, then the switch might not know about that destination address. It might not be in the table, and so it'll send the frame out on all the ports, hoping that it gets to its destination. Okay, so let's take a look at how these switching tables are set up. As you can probably guess, if you have a single switch in a LAN, each port is connected. Let's say there's no hubs or anything like that. Each port is connected to a LAN station. And so what you will have is a situation like this, where you have a whole bunch of MAC addresses, and however many MAC addresses you have, you'll have that many ports in the switching table. Of course, you'll have, physically however many ports the switch has, but if there's nothing connected to them, there's not going to be anything in the switching table for those unconnected ports. And also the other thing is, so remember, you'll have as many MAC addresses as you have active ports. And so that also means that there'll only be one, each port number will be unique. That's how we say it in computer science. That is, you'll only have one switching table entry for each port. That's only if you have a single switch for the entire LAN. Okay, so that's a simple case. More complicated case is when you have a LAN with multiple switches. Then you have a little bit more complicated situation, because remember, let's say switch 2, since this is connected to 3 LAN stations and the switch, each of these LAN stations will only appear once in the switching table for switch 2. However, in switch 1 will see traffic, will see frames sent from these LAN stations over here, connected to switch 2, and then switch 2 will send that traffic on to switch 1. And what switch 1 sees is that there's frames with different source MAC addresses that's connected to that one port. So let's say switch 2 is connected to port 1 of switch 1. Then what switch 1 will observe is that as it sees frames coming in from these various other LAN stations connected to switch 2, it'll see many frames with different source MAC addresses, but they're all coming in on that one port. So that's why we say that if a LAN station has more than one switch, some of the tables will probably have more than one MAC address for a single port. And so this is an example where switch 2 is connected to port 1 of switch 1, and in switch 1 this is the switching table. Switch 2 will have a totally different switching table. But in switch 1, what it sees is that on port 1 there are frames coming with multiple or different MAC addresses. And so it can only observe this traffic and see that, well, there must be at least 3 LAN stations somewhere down the line that's connected to port 1. And it turns out these switches are capable of handling a lot of MAC addresses. It's not like the 48 port switch can only handle 48 MAC addresses. No. Typically they are over capacity. They are capable of typically you can have 8,000 MAC addresses on a single switch. That's not uncommon. You only really need that if you have a whole lot of switches with 48 ports connected to each other. Typically we don't need that. Typically we have, especially downstairs, we only have a handful of LAN stations connected to each switch. It's only going to be a handful of entries in each switching table. You don't need 8,000 MAC addresses that you have to track in a single switching table. But it's not that expensive. It's just RAM, and so it's very easy to keep track of very large networks. Of course, you don't want to do that because then your broadcast domain gets large. You see a lot of broadcasts that clogs up the network and so on. Okay, so switching tables are not just created and then sort of written in stone for the rest of time, for all eternity. No, as you probably have done in the lab, you can disconnect a machine from a switch and then plug it in a totally different port and things will work. Well, how does that work? So the way switches handle that is that it will keep track of the time at which that switching table entry was set up, and then after a certain amount of time, it's called the aging time, it will say, okay, this is stale information and it's unlikely to be good, and so I will discard this. And so what happens is that if you have as when you power on the switch, you're learning, you see source MAC addresses on certain ports and you enter that into the switching table, but then there's a timestamp so that if some machine hasn't transmitted a frame for a long time, that means that entry will expire in the switching table, and the switch says, I'm going to forget about this one connection because I haven't heard any traffic from it for a long time. And so the switching table will actually forget old machines that haven't sent any data. And so on the other hand, if let's say there's a machine that's constantly sending frames, then every time that switch receives a frame from that one device, even if it's already in the table, it will update the timestamp. It'll say, okay, I got one message from it just a minute ago, and then bang, you get another message, another frame from that same machine. You update the timestamp. So that if you have a machine like that that's always transmitting, it's unlikely to age out of that switching table. If you have a machine that's not transmitting anything at all, if it's disconnected, then that entry will ultimately age out, and the switch will expire. That we say that the entry has expired, and the switch will remove that entry from the table. So that's how it keeps track of things like people unplugging a machine from a port and plugging it in somewhere else. It's always learning. Okay, so let's just take a quick look at advanced switches. And the topic we are going to look at is, it's actually not that complicated. The idea is that you can have virtual local area networks. And the idea is that, let's say you have a 48 port switch, but you're only going to have, let's say you use that for one LAN. So that means that LAN can have 48 machines directly connected to that switch, roughly speaking, because you do need one for the router or whatnot. But let's ignore that. Let's say roughly we have 48 machines in that LAN. Now let's say we have to segment that LAN and you have a whole bunch of subnets, but then we would, ordinarily we would say we would need a separate switch for every separate LAN and then connect them up using a router. So people did that a whole lot, so much that ultimately people said, well, wait a second, what if we put in some software into the switch so that we can configure uh, ports 1 through 24 to be one VLAN and ports 25 through 48 to be a totally different VLAN LAN. Then you can support two local area networks with one switch. So you sort of minimize the number of amount of hardware that you need. But it turns out when you do that, you do actually have to have a router connecting those two VLANs if you want those VLANs to be connected. If you don't need them to be connected, then yeah, you don't need a router. But chances are every switch is connected to at least one router. If you have a switch that's capable of VLANs, virtual local area networks, then you have to have, most likely more than one router. Two routers, probably. Okay, so once again, VLANs allow us to separate a switch into sort of two virtual switches. But if those virtual switches, if that hardware switch is not new enough, it can only do VLANs, then those VLANs are not connected unless you have a router. These days, you actually have much more capable switches that you can do the routing internally. We're not really going to talk much about these advanced switches or layer 3 switches because it's just complicated and it's not, we're going to avoid it except for this one brief discussion. So you might ask, like, well, it sure looks like if you have switches that are capable of VLANs, you can break a big network into a whole bunch of smaller networks. Is there anything more that you can do? Well, it turns out the main reason for using VLANs is to make it so that, let's say you have your team, you say you have a big organization with teams, let's say computer science people are in building 1, building 2, and building 4. Let's just say, just for an example. Then if you normally what you would do is you would have a switch in each one of these buildings, and that switch would be connected to people in that local area network. If, however, you have VLANs and then you have routing and all of that, then what you can do is you can have the computer science people in building 1 be on the same VLAN as computer science people in building 2 and building 4, so that they look like they are connected to the same switch, but what's really happening is that you have, 3, 4 different switches partitioned into separate VLANs, all connected using a router. And so why would this be an advantage? Well, let's say you have computer science people in these 4 different buildings and they want to share and be on the same domain. You can have a single domain controller connected to VLAN 1, basically allowing people in each one of these, each VLAN or VLAN 1, everybody in VLAN 1 in these different buildings can use one server and have things like file sharing, printer sharing, all of that, using a minimal amount of hardware. So you only have, in this case, 4 switches, and you can accomplish all of that. And you can have teams that are separated. you do need a router to communicate between the VLANs in a switch. And the reason for using something is like you improve management. That is, you can have a single domain controller for a team that's distributed geographically. So it used to be that when you didn't have VLANs, your teams were, if you have people in building one, they were basically on one network. Now you have virtual networks that are not limited by geography, by physical location. So this allows administrators to group users and resources, that is logically by, like, let's say department. Let's say you have computer science people spread out in different buildings, and then another department like health in also spread out in the different buildings. Then you can actually set up a server for each group even though they're physically separated. So group users and resources logically instead of just by physical location. So you're no longer constrained by geography or location of these teams. Okay.